Okay, I'm now ready to consider the very important condition that exists with binary stars that we referred to earlier, namely that they orbit their center of mass, which is like the balance point of a teeter-totter. So we have different masses or the same masses. In any case, one mass, say the smaller one, is an appreciable percentage of the other one. So all bodies orbit their common center of mass. That's always true. If you throw a hammer into the air and spin it, it will orbit at the pivot point near the head of the hammer. The center of mass is similar to where a teeter-totter would balance. So that's a good way to think about it. Now here's our star of mass m and little m separated by distance d. And we have this center of mass that we're trying to find. Here it is. Now the way I'm going to define this is to consider that orbital radius r is the distance from the center mass to the large mass. Just call that r. Now from the center mass to the small mass will be some factor of r. Maybe it's double, maybe it's triple, maybe it's something complex in between. Actually, in reality, because we can't choose our masses in nice simple multiples, this will be some complex factor of, or coefficient in front of the r. But in any case, the reference is to consider that small orbital radius between the big mass and center mass is r. So then x here is just d minus r. Separation distance between the two divided minus the radius to the big one from the center mass. All right, let's look at Newton's form of Kepler's third law. It gives us r cubed over t squared, but I'm saying the radius is really what we're talking about, is the separation distance. D cubed over t squared is g. You have to add the masses over 4 pi squared. Right. Now, the torques about the center of mass are equal, as seen by this situation. This kind of counterclockwise twisting force is equal to the clockwise twisting force of this. So that's another way to think about it. And so, like, if you're balancing this whole system in a gravitational field, you would relate that to this system. You've got an invisible, really rigid bar between here, and it pivots about this center of mass. So this force times this distance is equal to this force times this distance. That's why I can now say m, because mass is proportional to weight, times the radius equals little m times x. So mr equals mx would solve the torque problem in a uniform gravitational field. And that really does solve this situation. Now x is just d minus r. So we have x is, if you solve for x, we got mr, big MR, over m. So that's also equal to big M over little m times r. So I like to write it in this form because now we see what x is. We're going to compare x with this r. What factor is this orbital radius equal to compared to this one, this r? Well, it's the ratios of the masses, big M over little m. So isn't that nice and easy? Very simple. The ratio of big M to little m times this distance gives you this distance. Okay, so that's pretty practical. So we have x in terms of r. R is the distance to the center of mass from the larger of the two masses. Now getting just a little more into this. The center mass is actually the mass-weighted average position. The mass-weighted average position has a particular formula, expressed in a non-calculus form. It's the sum of all the individual mass particles times their radius, their radii, over the total mass of the system. Well, we can think of having 2 point masses here. One right there and the other one right there. So let's find the center of mass using this formula. If we look for the center of mass, we're starting from the big mass and we're going to find the location to this. So it's equal to r, this thing here, from here to here is r. That r is then the mass of each individual particle. The first particle is big M. There it is, big M. But we're starting there, so there's no radius at that point. Then we're going to add this mass times its radius. From here it's d all the way over here. So m times 0 plus m times d over the total mass gives us md over m plus m. So we now have an expression for x in terms of r, and we have an expression for r. R is this whole thing. So let's bring those together. So this is r, so we're going to take this thing and stick it in for this r. So think about multiplying this whole thing by big M over little r. I'm sorry, big M over little m. The little m's will go away and we get the big M left. So it's big MD over m plus m. So I just substituted this for r, and I got big MD over m plus m. Gives us the distance to the actual extent of x, which is from the center mass to the small one. Not in terms of r. Here it is in terms of r. I'll submit to you that this will probably be more useful because you'll already know what r is. I'll call r r. And then you just need to recognize that x, the other one, is just this ratio here. And really, having said all that, just remember this and you're good to go, almost always, with the problems I expect you to do with this. Now let's do an example using these ideas. So here we have a binary star system. The large mass is 4m, the small mass is 1m. And there's a center of mass, and as I indicated, the distance is r from the center mass to the large one. So what's d and what's x? And we're going to do all this symbolically. There's no real numbers given actual masses. There's no numbers given actual meters or kilometers or astronomical units for orbital radii. So we don't worry about that. We're just going to come up with an expression given the data we have. And then the starting point is for the center mass. At the center mass, this mass times this distance, m times r, equals this mass times this distance, m times x. And x falls right out. Look how easy it was to find x. 4r. So we have 4r from here to here, 1r from here to here, so the distance, the separation, is 5r. Okay, we're on a roll now. We can get all the other stuff we need to do here. The orbital radius of the small star, which we just did. The separation distance d we just did. Now the orbital speed and the period of their mutual orbit. The orbital speed of the 4m. This one, this orbital speed, is going to be obviously more. So it's got to go, well, 4 times the distance in the same amount of time. So it's going to go 4 times as fast. But I'm getting ahead of myself. What's the speed of this one? Well, we're going to use our super duper powerful problem solving idea, Fc is equal to Fg. And so mv squared over r is gmm over r squared. So you're comfortable with this right now. But what you're not comfortable with at the moment is translating this to fit this situation here. So that's what I'm going to do now. So you get comfortable. Remember, anything is easy to understand once you understand it. So the mass of the object that's moving, we're considering this mass. This mass is actually 4m. So I'm putting 4m for this v. The v we're talking about is the v of the 4m, so v of 4m squared. And the orbital radius is not the separation distance, because it's orbiting the center of mass, and that distance is r. This is r right here. So there's the Fc. The force required for this body to orbit this center mass. And that is equal to the gravitational tug between these two. What's the gravitational force? It's the force of attraction between these two masses. So that's G. Now big M is really this 4m. So we got to be careful. I know I show cap m here. This is general for the larger mass. the larger mass in this situation is 4m. So there it is. So yes, I'm saying 4m equals m. Because really this was a general meaning. Here particularly, it's 4 big M, where big M is really the mass of the small one. So there's small mass, big M. Okay. And then the separation distance is what this is. And that's 5r. So r is really like the distance. And the distance is 5 radii, 5 of these radii squared. So there it is. Now the 4m's go away real obviously. And so we have v squared over r equals g m over 25 r squared. You might have seen faster than that one of these r's go away. Well, they do. So there we go. And we get v of 4m, taking the square root of gm over 25r. Now I'm going to ask you to validate that if you apply this same idea to the small m, namely cap m, that you'll get this. V of that, now it should be 4 times the other one, but if you go through this exercise and pertaining to this one, so we'll have a different FC than we show here, you'll get square root of 16 gm over 25r. And now let's solve for the period. You recognize that the period is the same for both because you can't have one orbit the other without the other orbiting the first. So they both orbit the common center mass for the same amount of time. So let's consider that we're calculating, well, we can do either one because they're the same. All right. So I'm going to do m 4 pi squared r over t squared is gmm over r squared. We're going to get this. Okay, so we have to apply it to the particulars. Now we can choose either one of these as the particular. I'm going to choose the 4m. But I guarantee you'll get the same answer if you choose this one. You got to be really careful. The m of the object that's orbiting is this 4m. So 4m, 4 pi squared r, orbital radius. This is the orbital radius over the period squared is g big M little m over separation distance squared. There we go. 4m's go away. Now, here's it simplified a little bit. And I'm going to now bring this up over here and flip this thing around. Well, I'm not going to flip it yet. So 4 pi squared times 25r times r, 25r squared times r, 25r cubed equals t squared times gm. Okay, we're ready to solve for t squared, which is 4 pi squared 25r cubed over gm. Square root the whole thing. And there it is, folks. 2 pi square root of 25r cubed over gm, which looks a little bit different than our past expressions for period, given an orbital radius r and g and m of a large central body. Okay, so again, I will guarantee you, if you set this up to solve for the period of this mass, then, you know, the m is just m, one big M, 4 pi, but this is 4. See, the 4 comes in here, 4r over t squared. So that 4 would get transposed from here to here. You really do get the same answer. So this is how you solve binary star physics problems, and I'll expect you to be able to do this. So review this as necessary.